My name is Sydney Carr. We are Team Orbis 13. The objective of our project is to observe the Milky Way galaxy using radio astronomy. In order to do this, each of our 5 team members has constructed a radio telescope using a software-defined radio, a filter and low noise amplifier, and a uniquely designed antenna, which is designed to capture the frequency of the hydrogen emitted by the Milky Way at 1420 megahertz. We are using 3 different types of antennas: the horn antenna, the Yagi-Uda antenna, and a dish antenna with a circular waveguide. So far, we are able to observe the Milky Way galaxy in real time with 2 of our antennas, and we're working on doing that with the rest of them.
Hi, my name is Yuri Konetsky, and this thing right here is the Yagi antenna that I built. Right now I'm going to plug it into my computer. I'm going to run this program called SDR Sharp, and hopefully we're going to see some radio frequencies produced by the Milky Way galaxy at 1420 megahertz. This Yagi has 7 elements, all made of copper wire. This one has a folded dipole. A coax cable is soldered to the folded dipole. The coax cable is then attached to an LNA filter. Then it's connected to a DC block. And the DC block is connected to the SDR. The SDR is connected to the computer. The computer is running SDR Sharp. And as you can see, it is producing some results. A few bumps here at 1420 megahertz. Only problem is there shouldn't be this many bumps. But with some troubleshooting, we can solve this problem.
Hi, I'm Eric Ornberg, and I chose to design my system with a horn antenna. It's constructed out of mostly household goods to reduce cost.
I am using SDR Sharp GUI with an FFT averaging to see the signal in almost real time.
To isolate the signal, I first calibrate with a noise floor scan without the antenna attached. Once completed, I connect the antenna and hydrogen line signal rises above the noise floor. This bump will shift left or right according to the pointing location of the antenna in relation to the hydrogen cloud. This allows us to zero in on the cloud location. From here, we will record our data in a wave audio format, which we will use to process and map the galactic hydrogen cloud.
In addition to troubleshooting the Yagi antenna, our team is to start recording with the antennas that we do have working starting this month. We are going to take short bursts of data pointed at one angle above elevation and one azimuth angle. In between each recording, we are going to change either the elevation or the azimuth angle. And then acquire the data from that, import it to MATLAB, find out the magnitude, and we are going to use that to create an XY plot of the magnitudes. And we are going to stitch those together and do a map of the sky. Our final demo, we are able to show that map that we have created. We are able to show off some of the antennas that we used in our recordings. And then if we are lucky, we are able to do a demonstration. However, we would have to go outside and the Milky Way would have to be in line of sight for us to do the physical demo. But we can show video demonstration of our working antennas.
Hi, my name is Sam Cross. This is my circular waveguide dish antenna. So in summary, what you've seen today are demonstrations of 2 of our antennas that are able to detect the Milky Way in the sky. One of which is the Yagi antenna, another is a square antenna with the horn waveguide, and the next one is the one behind me, the parabolic dish with a circular waveguide. All these antennas are being utilized to capture radio frequencies that are being emitted by the Milky Way, can be received by this component, interpreted by the software-defined radio dongle, and being filtered out by our low noise amplifier, specifically tuned for the hydrogen frequency. We're very excited to move on in our project in the pursuit of stitching together our information, our data we receive from these antennas to make our 2-dimensional image of the sky, and looking forward to sharing that with you soon. Thanks for watching our video.